It's nice to meet many friends, and thank you for having me and all of that. Okay, so again, so what I want to talk about today are lab numbers from black holes. You have an expert here sitting in front of you, so you probably heard something, but I will assume that you don't know, and I will explain that. In the same way, I didn't know what lab numbers were until about 3 years ago.
I'm sure the same is true for the boss.
And and the reason I got interested in that was that it was brought to my attention that this number might actually be measured at some point. And so this sort of caught my interest, and I will tell you, hopefully by the time that I finish, you will understand why. And the talk today is based on 2 papers and ongoing work with Yotam Sherf, an excellent student at the university, and also with my collaborator, Joey McVeigh, which has been going for quite some time. And so what I will tell you first is what are lab numbers. Then, as I'm sure you heard, that they actually vanish, these numbers vanish for the GR black holes. So this makes them a focal point of interest, because if they are measured and found not to be zero.
And in your terminology, we live in 4D.
I think so. No?
Okay.
You don't agree?
No, 3 + 1, 4, whatever.
Oh, it's still okay. Yes, 4D is 3 + 1. And yes, so this actually makes them a focal point, and in fact, there is interest now in this type of quantities from several directions. One is these numbers appear, if you look at it in GR, they appear at order 5 p.m., which has not been calculated yet. And so we need a new method for calculating these effects in GR so that they can be separated. So it's like the background at the LHC, and it's actually the same people who are doing these calculations, the amplitude people. So that's the other are, of course, gravitational waves experimenters, GR.
Sorry, I totally missed it. What's the point of computing the lab numbers if they only exist in the quantum
no,
regime?
You calculate 5 p.m. effects so that you know I will explain that, the gravitational wave emission spectrum to enough accuracy so that you can tell whether you have an additional effect of the lab number.
Of BSM physics or deviation from GR?
Yes, deviation. So BSM here is deviation from GR. In fact, you see that there's a shift. And it's the same idea. It's the same idea. You need to calculate the background to enough accuracy, and that requires really sophisticated techniques. And there's also now recent interest from the more formal theoretic community in relation to ideas about quantum black holes and so on. So it's really like a focal point of interest.
But can I clarify one thing? So if they don't exist in the classical level, and surely emission of actual black holes is classical, this whole thing is driven just by mathematical curiosity. It has nothing to do with the actual emission.
If you wait long enough, you will see that it's actually physical reality and not mathematical.
Okay,
curiosity.
nice to know.
Yes. Okay, and so then, right, I will go on to explain why and how to calculate lab numbers in the quantum case and discuss whether they can be measured in gravitational wave experiments or not. And for those of you who are interested, the appearance of non-vanishing lab numbers is also related to the appearance of additional ring-down modes after a black hole merger. So there are ways of constraining both of them from the same idea. But I will not talk about it today. So we go on. Do we go on? Yes, so first, the standard expectation, which I want to try to convince you is not quite correct, is that if you have these big objects, the black holes, they are classical and we will not observe any quantum gravity effects. Now, what my premise is that black holes have to have some internal structure because of we know that quantum theory persists also for black holes. They have to be unitary, and so they have to have some internal matter. I don't want to discuss it too much. It's just my basic assumption. And so in this case, what I expect is that black holes have an internal structure, and this leads to some observable effect. And the question is, what is the strength of this observable effect? Okay. And there are many discussions, I don't know if you follow the literature, about phenomenology of deviations from GR. There are many that you should not discuss, but this is again another topic. Yes, so the reason, as I said, the expectation is that quantum gravity effects are irrelevant to the black hole, astrophysical black hole. And this expectation is based on the idea that the parameter that the small parameter that governs the deviation from GR is L Planck over the scale of the black hole, L Planck over Rs. This is true when the black holes are in equilibrium on the ground state. But what I argue is that the small parameter that is relevant for deviation from GR is actually the amount of excitation energy. So you take a black hole. I view the black hole, not the external black hole, as the ground state. It gets excited, for example, during a black hole merger, or when in an in-spiral phase, there is an external field that acts on it. And the amount of the small parameter that determines the deviations is the amount of excitation. In fact, if you look at what LIGO measures, it's exactly that energy. The quadrupole formula tells you that it measures the emitted energy from the excited state to the ground state. And that quantity, this delta E over the mass, it is small, but can be finite. For example, in these black hole mergers that LIGO observes, it's a few percent.
But this is just the excitation of the horizon, right? Some quasi-normal modes.
No.
This is purely classical.
Yes,
thing.
yes, but in this case, in GR, it's just the excitation of the quasi-normal mode, but I argue that if black holes have structures, also that the internal structure would be excited.
So you claim, in some sense, that quasi-normal modes will not behave classically.
No, the quasi-normal modes, standard quasi-normal modes are excitation of space-time away from the horizon. They will remain also in this case, but there will be an additional branch that is similar, for example, to fluid modes of neutron stars, and that will induce correction.
And so your claim that the ring down will not be will not be describable just by quasi-normal modes,
No.
by some enigmatic quantum.
No, it will be, in this case, since this is not the subject of one talk, but when you ask, I will tell you. So in this case, there will be a prompt branch of quasi-normal modes that are the standard quasi-normal modes. And in fact, there will be long-lived additional quasi-normal modes starting sometime after the merger, separated by time from the standard quasi-normal.
But so it's strange that M-Planck doesn't enter at all in your parameters, so I'm concerned.
In this situation, in the equilibrium, this is the correct parameter. But in this case, you have a large excitation, so you can view it as a semi-classical excitation. Okay, now what do I mean by an interior? So this is supposed to be a picture of a black hole. It's not a picture, not of a black hole, but it still helps to visually focus the ideas about what I mean by the interior. So what I mean by the interior is the quantum state, right? The quantum state, the state of the matter that collapsed and fall and created the black hole. And there is some spherical object. And this is it's a visual picture of that object. So yes, and classically, as we know, this state is causally disconnected from the exterior.
So is that expression, I never given it any thought before, supposed to work both inside and outside, but just not at the boundary?
Sorry,
That expression for the metric, is
yeah.
that meant
So-
to be valid inside as well as outside?
No,
Oh,
that is
that was
something
the
that is
exterior metric,
outside.
okay.
And in fact, as we will see in the context of this talk, the only difference between a black hole and a quantum black hole are the boundary conditions on the surface of the deformed object. So you have some excitation, the object deforms. This is also true for classical black holes. And it's the boundary conditions for the equations outside on the surface that,
I see.
and in fact, it's a single
Very
boundary
sweet. It's
condition.
something like the way monopoles evade the decoupling theorem.
Right, and it's a single boundary condition. That's the amazing thing about that in the case of the lab numbers, the electric lab numbers.
I thought Schwarzschild works inside quite well. You just need to reinterpret the parameters.
So you do that, I do something else.
Yeah.
Yeah, for some reason, it's not working, probably because of the Zoom. It's supposed to.
There's a delay.
Maybe. There's a simulation. This is a simulation of LIGO, and this should be anyhow. So doesn't matter. This was supposed to ring around, and this is a view of the deformed horizon as it oscillates due to an excitation. Okay, so this is during the merger. During the merger, you have a large excitation and decay to equilibrium, and during an in-spiral, you have small transfer of energy if you have an internal structure, small transfer of energy from the orbit to the internal degrees of freedom, and that is the mechanism that allows you to do it. Okay, so what are lab numbers? Lab numbers are just the classical gravitational progressibility of compact objects. Lab is a name. It's the name of an English mathematician who studied first tides on Earth. And because these are tidal effects, these are called lab numbers. And they were studied for quite a long time, not such a long time. And then in the context that they are thought about is in the context of an in-spiral, a binary in-spiral of a binary compact stars. one of them exerts a force on the other because the frequency of the rotation is much smaller than the natural frequency here. You can take the limit, the static limit. So it's as if you are having a static gravitational force acting on a compact object. And the lab numbers, in this case, I'm focusing on the L equals 2 electric lab number. You can do the same for the higher L's, and there are also magnetic lab numbers. Sergey knows very well. And
Not to be confused with real E&M.
yes, but they are just the analog of the electric and magnetic part, in fact, of the Weil tensor in this case. And in this case, the reason that I focus on that is because this is supposed to be the largest one. And if there's any chance that something will be measured, it's probably this one. So I'm focusing on it, but it's possible to do it. Okay, and so you see, you calculate the force, the force field on an object from the other partner. There is some, this is fixed by the external field, this term. And this is fixed by the external field, and this is the response of the object to the external field that is exerted. So it's the complete analog of electric polarizability. Okay, and there are numerical factors and a sign that are conventions, so that the lab numbers for neutron stars come out to be positive. Okay. So now,
And that R was the radius of the compact object.
right,
Separation.
yes. Thank you for. It's by now
You're so
I'm
used
so
to it,
used to
right,
it.
right,
So please do that also as I continue, because it helps me.
Okay, thank you. I just remember I was confused. I
I know.
with others in the audience.
Yes. So the way that you so this is the second important point, is that they vanish for the four-dimensional GR black holes, and this was known by calculation for a while. People just found it, if you wish, by brute force calculation. You saw what you do in general in this case. You sort the Peter-Brighton equations, you put boundary conditions, and you just check the different powers in GTT, and you find the coefficients from there. So it's a completely straightforward calculation. And they found that it's zero. And the reason that it's, well, this will become here. And then recently, Sergey and also Lampoud from Colombia noticed that this vanishing of the lab numbers is associated with Sergey associated that with a symmetry. I'm sure that you heard about it, and Lam is doing something that is somewhat different, but they explained why the lab numbers vanish to some extent.
But it's not something which you can explain to us in 3 minutes.
Sergey will explain to you.
Not in 3 minutes. I remember I asked him.
Okay.
It's not something obvious.
No, the simplest explanation is that you solve, right, it's a second order equation. You have a decaying and an increasing mode towards infinity. And the lab number is the coefficient of the decaying modes. And if in GR black holes, that decaying mode is singular on the horizon, and so you need the coefficient needs to be 0, and that's why the lab number is 0. That's the simplest technical explanation. But I think the explanation that Sergey has, and also to some extent Tom, are much nicer.
Disconnected.
I got this good. So what should I do?
Just like there's some parts that are being explored and
No, it's not. General dimension for short intervals. They actually do vanish for some subset of L's for orbital. So because in our explanation, the dimension is not that different.
Sergey, but it's not something obvious, right? It's not something which you can feel in your guts, no? Right? It's just you can prove it, but you cannot feel it.
No, it's very puzzling.
Oh, it is puzzling.
Because it kind of tells that the whole behavior essentially is like point particles. There are no high order static responses.
It's special to 4 dimensions, Sergey?
Not really. In high dimensional black holes, lab numbers vanish for some subset of orbital numbers. At least in our, I wouldn't call what we did as explanation, but observation. So that there is some approximate symmetry, and this vanishing of lab numbers is associated to like highest weight properties of corresponding representation. And so the symmetry exists in any number of dimensions, but the solutions belong to highest weight representations only for like this orbital number taking special values in higher dimensions. But L for all else.
It's actually a very interesting structure. Okay, so now the thing is that with Blackboard, so typically what you do is you solve the perturbation equation on compact object, and the boundary condition that you put regularity at 0 and the continuity at the surface. But with black holes you can't do that. So you replace these two boundary conditions by some other boundary condition on the horizon and at infinity. Okay. Okay. Now, in this case, in GR black holes, they do get deformed, but that deformation is not reflected in multiple moments at infinity, measured at infinity. Now, what is it that you need? So now it's moving. What is it that you need to have lab numbers non-vanishing? And again, I'm talking about 4 dimensions, concentrating on the electric quadrupole number. It's that either you need new internal fluid-like modes, so there is a physical deformation of the object, or no horizon, or both. Okay? And this quote that I have here is that the difference between this case and the GR case is that deformations do not produce physical effects for observers at infinity. So now I'm moving to my quantum lab calculation, and I want to remind you this will be very similar to the electric polarizability of a quantum atom. And so I want to remind you how this is done. Sakura. And so what happens is, right, we have an atom, it's neutral, you put an electric field on it, it gets in quantum terms, the ground state gets mixed virtually with the excited states. And the result is a non-vanishing electric polarization. And the coefficient of that electric polarization is called polarizability. And the lab numbers are just these numbers for gravity. And you see it's a second order time independent perturbations. In fact, looking at your paper after our discussion, I think you have a diagram with 2 Qs. which is similar to this. So, right, so now I repeat the same thing for quantum slab numbers, quantum polarizability, gravitational polarizability. So the interaction now is as indices. You can remove the indices by looking at tensor structures. And what I'm interested is in calculating the induced quadrupole in the ground state, so for the black hole. And the relationship between the coefficient here and this coefficient is like so. Now, it turns out that for quantum black hole, in general for very compact objects, the K2, the lab number comes out negative. In fact, that's interesting, and it's related to how the mass function, as a function of the radius, works. Okay, so this is also something that was observationally found.
And here, m of r is the mass inside radius r.
Yes, yes. So
And when
it's
you
the
say
mass of the object.
increasing as you go in,
No, so
because like for a neutron star,
again, let me explain. So for black holes, you have a solution for each value of the mass, right? You have black hole. And then the question is, how does the radius change when I increase the mass? Or how does the mass?
the Schwarzschild radius.
Yes, so that we know. Now for neutron stars, you can increase the size is limited, but you still have some variation in the mass. And it turns out that the mass actually, what did I say?
It's not even known, right? It may have
Well,
curves in it.
Yes, so, but for example, Thorne actually claims that this is the case, and from the science that I see, it actually.
But I mean, if you look at models of the equation of state, some of them have it being sort of what you would expect naively.
Right.
But others actually it turns around and
Okay,
it's
so
not
in
excluded
that
physically.
okay, so that's actually very interesting, because this might have also some relevance for neutron stars, because this is a way of probing also the equation of state at the core, which, as you pointed out, is unknown. In fact, if you think about what the options, they're not that great. And it really needs to be very exotic matter.
But it cannot be that simple, right? Because for a
No.
neutron star, you have crust,
No,
and what you call radius has nothing to do with the resulting gravity, right?
No, it
It's
cannot
all
be
much
that
more
simple.
complicated.
Much more. Okay, so let me go on. And now, so what I do is I calculate the polarizability using second order time independent perturbation theory, and I get a similar relation to the lab number, if depending on the internal structure of the black hole.
Except now I don't understand what are the quantum numbers n, m. They are to indicate some state of a black hole somehow.
Yes.
But what exactly do they mean?
So let me go on, and then I will try to explain. So what I will argue in this case is that the best way of thinking about it is, since we are looking at large excitations, I can use the Bohr correspondence principle and do semi-classical waves rather than quantum states. So this is the strategy. Okay, so in this case, now we don't know what the internal spectrum of black hole is, but this equation is telling you, given a model for the spectrum of the black hole, what it gives you the lab number in terms of that number. And in this case, you see that probably we expect that the spectrum, the microscopic spectrum of black holes will be very dense. And so I can turn it into a spectral function. And this gamma you see in this case, gamma is a parameter that tells you the quadrupole dimensionally has to be something like ER squared. And gamma is the parameter that tells you, is a numerical parameter, presumably order 1 or smaller, that tells you what is the actual quadrupole number. And you see that in this case, this object does have an H bar, and what I will be looking at are excitations that essentially have 1 over H bar worth of energy in them. So they will be semi-classical. Yes, so it turns out that and this is just here a justification why occupation numbers are large in the region that I'm looking at, and why I can use semi-classical analysis. Now, again, so the problem now is reduced to finding the spectrum, the internal spectrum of the black hole, of the quantum black hole, and then I use the Born correspondence principle to write classical wave equations that will reproduce that. Okay, and so here is an estimate of the quantities involved. Now I'm moving the quantum numbers are those of the coherent excitations, and I repeat the expressions that I had before, and I can now have an explicit expression in terms of these functions n of e, gamma of e, of the lambda, the quadrupolar lambda. And as usual in this case, we expect that the dominant contribution will come from the low-lying state, also because the quadrupole is expected to be larger. So, yes, so now I'm estimating, in this case, I'm using this approximation that there is some discrete spectrum of waves, similar to fluid modes of compact stars. And I'm taking the approximation that this sum is dominated by the first excited state. This can be, we checked it in some models and it looks reasonable, but at this point, I just want to show you that you get something which is not L-Planck suppressed. This is my main point, not so much the detailed values of the objects. And in this case, you see that you get something which is related to that frequency. That frequency is expected to be
1 over r.
No, so suppressed. There's typically a coupling, for example, in the string models that we looked at. It's a string over Planck, so G string squared times 1 over r. So there is some perturbative parameter associated with the additional scale of the theory that enters into this.
But what can this parameter be, right? Because if it is 1 over r, then it is over the unity, it is very interesting. If it is much smaller than 1 over r, then it is irrelevant.
Yes, so it's smaller than 1 over r, but not microscopically smaller. So let's say 1/10.
And this 1/10 is alpha prime of M Planck.
Something like in the string model, it's like that. We also have a model where this is a cavity, and I'll show you one explicit example. Yes. So again, so now if you come up with some model of a quantum black hole, I can relate it to a lambda. So here is a microscopic example. This is something, in fact, that I added after my talk on Monday in Colombia, because they asked me to do that. And in fact, this is a model that we used a long time ago. And the idea is to describe the black hole as a maximal entropy state. So each sphere in the black hole has maximal entropy, has Bekenstein-Hawking entropy. And if I assume that, I can write the density of state in a straightforward way. And in fact, you get an equation of state for this type of object, which is P equals rho, which is the equation of state of highly excited strings, long strings, unique equation of state, because this is in the general dimension.
Can I add something? In the slide before, we have like delta energy over the mass of the black hole.
Yes.
But we would say that because the black hole has a big entropy, has a lot of degrees of freedom, delta energy should be proportional to e to the minus entropy. So that is super, super tiny.
Yes, but you remember that what I said is that I'm looking at coherent states. So these are coherent oscillations, collective oscillation of many, many of these microscopic states. And these have energies that are small but finite compared to the energies of the. But here, I don't do that. Look, I just put the spectrum in, the spectrum that I found. It's really very thinly spaced because the total entropy is SVH. And I just do this integral. It's if this gamma of omega, remember gamma of omega is the quadrupole moment for a given energy. And this gamma comes out to be this quantity, which is the small parameter, but not microscopically small. And the r to the 5 gets divided by the definition of K2. And so we get something, you see, that is order 1, but smaller than 1. Again, I don't want to push that too much, but it's just an example of how this works.
Yeah, correct me if I'm wrong, but what you're calculating here is not a quantum correction to classical lab number. It's kind of just calculation of the full lab number recast in the quantum language.
Yes.
But then, and I think what you show is that, well, basically that's the usual argument that on dimensional grounds, so kind of one expects lab numbers to be, that coefficient to be order 1. But then, kind of, we know that black hole is described by GR, so, and that's kind of a surprise, but the calculation then as a result of doing the calculation, we get 0, they expect order 1.
Yes. So let me show you how this works in the standard way. This is coming next. Okay. So, and this is another calculation. You don't see it, but it's just to see that in this case, we model the black hole like a cavity with reflecting boundary from the inside, and then you can actually calculate that, and you get again something which is a small parameter, but order 1.
But wouldn't you admit that what you are doing is highly unconventional, right?
Of course,
because in the standard world, external field, classical GR, you get the answer, period.
I know, 0.
Right? So you agree that you
Yes,
are
yes.
really messing up with the standard wisdom.
I wouldn't call it messing up. I'm saying that it needs revision.
Right, okay.
So now I think I'm answering your questions. So what is the relationship of what I did to the standard calculation? And there are 2 ways of doing the standard calculation. One is using the geometry, the metric, you write perturbation equations, which I will show, and then you calculate you see there's one term that the induced one goes like r cubed, the external field goes like r squared. You know the coefficient of the external field, and you calculate the coefficient of the induced one by solving the perturbation equation with boundary conditions. Another method, which is more closely related to what I was doing, is, and I'm working in the Cowling approximation, so the standard quasi-normal modes of space-time, I'm ignoring it and I'm looking just at the internal fluid modes of the object. And this is done here. And in this case, I treat it as I will explain. They are treating this object as a collection of forced harmonic oscillators, and they can calculate the love number using this. So in a similar way to what I do.
Sorry, can I ask? So if you do this calculation, like if I were to do it, I would simply require that there will be a non-singular horizon. I will never go beyond the horizon, right? Oh, okay.
So I'm doing this. I'm ahead of you. Okay. So this is the standard calculation. You see this, there are three perturbative quantities. One is the GTT, GRR, and the angular part. The spherical symmetry forces the two H0 and H2 to be equal, and then you can just solve the equation in terms of this parameter X, which is a 1 on the right. And so you get some kind of the expansion, you get a C1 and C2. These are the parameters that are associated with the increasing and increasing mode, and K2 is the ratio between. Okay, so that's the standard way. And so, and as you will see in GR, what will happen is that the C1 will be 0, and in my calculation, C1 will not be 0. And another way, which is closely related to what I was showing, is as I said, describing the oscillations of the fluid or the object, the internal oscillation in terms of a bunch of Lagrange deviations, and they satisfy simple force harmonic oscillator equations, which I teach in my physics 1 course, so I should know. And there are explicit expressions for all the quantities, and recall that we are looking at in the static limit. So this omegas, the omega is much more than omega n. Omega n is the normal frequencies. And I can repeat this calculation and get a value for K2, which, as you can see already, is closely related to the quantity that I calculated. It has the same structure. And it's also useful to define this quantity, the induced energy. I go through the calculation, and I also defined on the way, I think the internal energy is just the harmonic oscillator energy per harmonic oscillator, and I substitute into the original equation. I assume here also that the dominant contribution comes from the low-lying state, and the simplest approximation is just assuming that it comes from the first excited state. And you see that you get an equation which is very similar to the one that I did. Now, the two methods have to agree because they calculate the same quantity. So this way you get a relationship between the spectrum and the boundary condition that you have to impose on the deformed surface. It turns out that if the spectrum doesn't exist, the boundary condition is C1 equal to 0, and then the love number vanishes. And if you have a spectrum, you have a real deformation. C1 is non-zero, and the love number doesn't. And let me show you how it's done. But before that, I'm not expecting you to read it, and I will not read it also, it's just showing that we sort of discussed very explicitly the conditions under which this type of comparison is valid, and we argued that it is valid for black holes. And the main assumption here is the same assumption that I used before, is that I can describe effectively the interior of the black hole as a collection of waves with a discrete spectrum, which is something that you get in reasonable moments. Okay? And
These
then
modes you're concerned with are all higher L modes, right? If they were just
we can do this.
strictly
Yes.
symmetric, it would do nothing.
The reason that I'm looking specifically at L2 is because this is the one that couples to gravitational waves and can be measured.
Right.
But you can do the same thing for all the higher
I mean, it
elements.
wouldn't have, they would be sort of stuck there, is that right? And they
No.
would last forever, it would never reach
No,
end?
no, they have expressions that are very similar to this, and in fact, they're usually suppressed. And also you have a magnetic type.
I just was thinking of maybe I'll ask you later.
Yeah. So you can repeat that for, and they were also done previously, and you can repeat that for higher. You can repeat that for
I
the,
wasn't thinking of the calculation, but about the physical object. So if you make a more massive black hole by merging
Yeah.
two,
but you can
then you
imagine,
will have created a thing presumably with these modes.
right,
But the L=2 modes can radiate gravitational
Right.
waves and they'll go away.
right.
But then will the remaining object be staying there kind of vibrating forever
No,
because it
I
can't?
think that there is some coupling between say, the octopole and the quadrupole. There should be
I
some
was thinking
coupling.
about the monopole.
The monopole just means that the mass is increasing.
Why not just vibrating?
No, that's not allowed in gravity. There's no scalar mode.
Well, that's why I'm confused, because it seems like what you're doing would imply that.
No, I think this is a gauge mode. You can gauge it on the scalar mode.
But since we don't quite know what we are talking about, we
Okay.
can just
Yes,
say.
you can imagine, but that you have a scalar mode, but I don't. Okay, so
Quick question,
yes,
this model with the oscillators, is it claimed that this reproduces what we expect of the spectrum of a black hole?
no, what I'm saying is that if I'm thinking about coherent oscillations of black holes, so in that sense that's the spectrum, then I do expect oscillation. I do expect the spectrum. So think about this way. Suppose that you excite a black hole. Also in GR, it does have this type of oscillation, so quadrupole oscillations.
So these are excitations of the gravitons outside the black hole. It's not the quote unquote excitations of a quantum black hole.
But
Right.
in this case, since eventually what you measure are only quantities at infinity, you can tell yourself whatever story that you want as long as it's consistent with the result. So if you don't want to think about it in these terms and you have an alternative fact way of thinking about it, that's okay. But the point is, in this case, is that if there's a difference, the GR deformation does not induce moments at infinity, and if you have a real physical object that deforms, it does. That's the real distinction, and you can phrase it in different ways. This is the way that I phrase it. Now, here there is a discussion of what happens at the boundary. Again, I don't expect you to read it. There's a summary that we did here, and you can read in our paper the discussion. The point is that in this case, the boundary condition, if I want to reproduce this type of oscillation, is different. One single boundary condition on the deformed surface is different between the GR black hole and this in the quantum black hole with the solutions. Okay, so that's the difference. And the deformation is small, so you can do a perturbative expansion, and you can, in this case, find what the boundary condition on C1 that you need to impose so that you reproduce that answer, and the answer is, the way I would phrase it, is like so. So in this case, you see that the difference is in the boundary condition that you have to put on the deformed boundary. Okay, so now I'm moving to my last part, which is can love be measured? There's endless ways of playing around with this. I try to tone it down, but from time to time, I cannot resist. Yes. So, right. So the question is, in this case, is whether to what extent can a lab number, which is not microscopically small, but is order 1, probably like a 1/10 or 100, can it be measured? And the idea, how is it measured? This, as I said, the key element is that you need to transfer enough energy from the orbit to the internal modes. And to do that, because the amount that is transferred in each orbit is very small, you have to have many orbits. And that's why it's unlikely that a LIGO or terrestrial, even improved terrestrial experiment are measured, it's because they don't have enough, they don't follow the merger for enough time. So I'm thinking about LISA type sensitivity, and the parameters that I'm using are these, and you see this is something like 10,000 cycles that they can follow. These are reasonable number accepted as a sort of benchmark numbers when discussing them. And I'm taking you take 2 of the order of 1/100 or 1/10, and you see that in this case, what they measure best is the phase of the waveform of the emitted gravitational wave. That's what they're most sensitive to. And there are typically 3 contributions. One is it's the standard GR calculation. That's where the amplitude calculations come in. You need to do that very precisely. The tidal deformation, that's the lab number. And then there's also tidal heating, which I'm assuming for reasons that if you wish I can explain, that is small. And yes.
Sorry, are the lab numbers still 0 if I consider Einstein gravity with higher derivative corrections, like R4?
Yes, but in this case, we're talking about large black holes, so the value of this coefficient, this actually Sergei calculated, but the value is microscopic. If you assume that they are coming from fundamental theory at a very high scale, which I assume that you assume.
But is there a way to, like, you're saying the way, the form of the correction that you obtain is different from the form of correction of those corrections?
Probably not, but the strength is much larger. The whole point is that you don't get terms that are suppressed by M-Planck, but they're really they are proportional to delta E over. Okay. So, and there are standard expression in this case saying what is the tidal deformation phase difference when you have a non-vanishing lab number. They are here in the example. We actually use the explicit expression that the gravitational waves experimenters use. My student Yutan. And these are the parameters that we use. We assume in this case a binary at 2 gigaparsecs, so quite far away, and the mass of equal mass of a million solar masses, which is again something reasonable for LISA. And these graphs show this is, I think, this is 3 sigma value, the dotted graph. And so something below that is something that you might say detected. And you can see in this case, this 0.18 is essentially a limiting maximal value. You should ignore it. It just means that there's nothing below. But you see that what happens is that there are some cases where the results lie below the 3 sigma, so they are detectable. And you also, in this case, see that you need to have slight spin. Our calculation were for Schwarzschild black hole. We did some estimate of corrections for Kerr black holes. But these are the reason that you have this, that it's better to have spinning black holes is mostly because part of the energy of the spin is going to the orbit and then to the internal structure, and also because the innermost spherical ISCO, like innermost spherical, somebody help me? Okay. Is smaller for spinning black holes. So you can see that the way I would read this graph is see that it's not impossible to detect lab numbers of the order of magnitude that I presented. That's why I think it makes them very interesting. What we are doing now is we are looking at a very interesting possibility. I'm not sure how much it will be actually realized in experiment, but if there's a resonant effect between the orbit and the internal frequency, then you can put in much more energy into the internal structure, and that can enhance the effect. And what we checked, it's not a published paper yet, but what we checked is that it is possible to get to a resonance condition before the object becomes relativistic. So when these expressions that I use are valid. So this might be very interesting.
So
Okay.
again, I have the same curiosity. So that delta energy is the energy in the coherent states of the black hole.
Well, here now it's
no.
So now it's, in this case, it's actually the total, eventually, it's the total transfer energy from the orbital energy to the internal structure. So it doesn't really matter in this case whether the description that I describe in terms of this coherent state is correct or not. The only thing that matters eventually is how much energy is transferred into the internal structure. So if you don't like the wave picture, use some type of, for example, we could do it. I didn't want to mention it because I think it's not a good model, but we can do it for area. Suppose that you do area quantization of black hole, you get a spectrum, and you can do the same calculation for that. And if you have a better model of a black hole coming from string theory and so on, which I hope to have, then you can also put that in. And then these expressions are valid. And you just need to know the absorption, the rate of absorption of external energy into the internal structure. Okay, so in this case, you excite either virtually or real excitation of the internal structure, and then that gets emitted in gravitational waves.
And G was the fraction of the orbital energy that gets transferred. I forgot what little g.
No, this little g is this perturbative parameter that I called before gamma. So I now parameterize gamma in terms of the wavelength. And g, it's in the model. It doesn't really matter.
Well, it gives us an idea of
Yeah,
what
so-
physics you're talking about.
So in this particular model, also in the string model, that g squared is the spring coupling. So it's the number of order, let's say 110, 125, whatever. And it also, in terms of these modes, it is v squared over c squared. So these modes, the relativistic modes cannot exist because of the boundary conditions. And these are non-relativistic modes, and the amount that they are non-relativistic is that number. So it's some number, a small number, but not microscopically small. Yes. So with that, here are my conclusions, which are also the third slide. I hope that by now, at least, you know what lab numbers are. And as I was showing before, I argued if this picture that I described is correct, then they will be accessible to measurement. And what's nice about that is that if you know the internal structure, this means that that internal structure is also excited during a merger. And so it will also control the decay, the quasi-normal mode after the black hole merger, in addition to the standard quasi-normal mode. And we already did a little bit of analysis of that kind, like what you did. So thank you.
You talked about quantum black holes, but what's the difference between, instead of quantum black holes, I use the word boson star or Neutron star?
Yes. So
Change.
okay. So the general framework will not change. The difference here is that I assume that the object is as compact as a black hole, or now boson star cannot be compact with a black hole. It must have to be much larger, and so and probably doesn't exist, but that's another question. And so in that case, you will get the calculation will proceed in the same way, but the results will be different. I didn't do it for neutron stars. Okay, so let me say this. There will be an important difference if the object has a photon sphere or not. It has a If it doesn't have a photon sphere, then this type of calculation is changed in a dramatic way. Okay, now typically creating a compact object that has a photon sphere is very problematic, as I'm sure that you know there are lots of it needs to be composed of exotic matter, and it has to have special properties. So in that sense, there are not many options for this type of object. And in that sense, so in fact, we have now, following the same logic, we have what we call the frozen star, with some hint to how black holes were called before they were called black holes. And this is a classical geometry with which seems to be consistent with all the constraint, non-energy condition, and so on. And we can repeat this type of calculation. And there we do find in oscillatory modes. And so in that sense, this I think also what I answered to Ahmed, right? If you want to think about it in purely classical terms, it's okay. But The point is that I claim that in black holes of our world, they should have an internal structure. And then the calculation eventually, because the LIGO people they don't know quantum mechanics. They don't use quantum mechanics in their estimates, right? They just use classical GR quantum.
And it works.
Yes, so I should be able, in this case, this means that I should be able to describe everything that I do in classical term, and I just show you how to do it. It's just changing one boundary condition in this case. This is in spite of the fact that LIGO is the most quantum object in the universe, right? LIGO has a coherent state of more than Avogadro number of photons. So, yes,
Just to make sure I understood,
Yeah.
Is one of the punchlines that this effect is enhanced due to the Bekenstein-Hawking entropy or not? Can I think of it like that or not?
no, I think that this doesn't come in.
Well, you use it at some point. So
No,
I'm
I had this is because in Colombia and here,
Okay.
people were saying, okay, let's see some microscopic models. So
I see,
in that
I
case,
see.
I
Okay.
just show the microscopic model where it's really thinly spaced. And I show that in this case, all that matters is the integral over the spectral function.
But you have to put a density of states in there.
Yes.
What was important about that density of states?
So
What
in
did
that
you do?
case, there was nothing, as far as I know, nothing special about that. In true density of states, we have to insist that it reproduces the Bekenstein-Hawking entropy.
Okay.
And therefore, the true microscopic spectrum has to be very thinly spaced, right? Because the energy is in black hole, and you have to put e to the s states in. But this is, they're so thinly spaced, and you're putting in so much energy that's the details of that distribution, I think, are not important.
Let's just reproduce dimensional analysis as a object of size R. You expect these love numbers to be like given by for the 1 and 1 over R units. So sometimes I think that was the opposite of putting black hole physics. To me, it sounds like a statement. Okay, for generic object, you expect love numbers to be for the 1, but I don't see it where for actual black holes are 0. What's here?
So in this case, this is what I was trying to do in this showing how the spectrum and the lab numbers and affect that C1. So it's the form. The point is again that this is in fact common, as you point out. So if I did the same thing for a neutron star, imagining that it's compact enough so that it's within its photon sphere, and these most decoupled from the standard quadrant. No. I would get a similar result. So the key is whether you have some internal excitation or not. And if you don't have an internal excitation as the R black hole are, the lab number will vanish. And what I showed here is that if you do have internal excitations, then it comes out, the naturalness is restored.
Let us
Yes.
So basically, you are saying that certain observable associated with love numbers, like if one does this calculation differently, like this way, that it gets really order 1 different from classical GR answer. But wouldn't one expect that then all other properties of
Such as?
well, like quasi-normal.
So what I said,
also all
But
other
even worse,
even
the
more.
merger itself.
Right, the merger,
Because
yeah,
if
right.
those
Yeah.
internal
Right.
modes
Right.
affect the boundary
Right.
conditions, the merger proper, all calculations of Pretorius should be thrown away.
Because I don't see anything
Everything.
special from
Okay.
GR calculation. I don't see anything special
So
about that
let me-
particular.
Absolutely.
okay, so the particular thing is that you have something that looks like a horizon. So let me tell you how this is reflected in the spectrum of quasi-normal modes, okay?
I think Andrei is right. One should really talk first about it.
The event proper, the merger itself will be modified.
it will be modified, but I don't expect it to be modified in a significant way. Again, this is a too technical a discussion, but I can explain to you. I thought about that, and if you wish, I can.
What do you mean, where significant means it's like the square of the small number or something like that?
No, what I mean is that the merger will not be that different from.
What do you mean by that different? Would you say your love number is that different or not?
Okay,
When it's
so
a tenth?
let's discuss.
It's a
So-
semantic. If you say, is 1/10 different or not different?
Okay, so let me explain. First of all, I'm working towards understanding that question, so I cannot answer it specifically. But, so let me tell you how the calculations for the merger are done. So basically you have the inspiral. Up to the E-score is something, it's Newtonian gravity, so this should not, this doesn't matter. And from a few Schwarzschild time after the merger, this is again Newtonian gravity. The difference in that case, I can explain, it's a small difference. So you have basically a time of order, a few Schwarzschild radius, where anything that you change can occur. Now, typically what they do in this case is that they just interpolate between the two. That's
They
the
meaning LIGO.
LIGO, that's the standard way. And since the, you know, you get very close to each other, sometimes even pass, because you can do this type of extension from the final stage. So in this case, there is only a very small window where something could actually be different. And in that small window, I expect some corrections, but not that much. But I don't know what the answer is. Now, for the quasi-normal modes, what happens is that you have, I mentioned initially, you have the standard quasi-normal mode coming out in a time scale of Schwarzschild radius after the merger. And these additional modes depend, now it depends whether the final object is rotating or not. If it's non-rotating, you have an additional branch of quasi-normal modes at very low frequency with very large lifetime, with a hierarchy between the frequency and the lifetime. The lifetime is much longer than the suppression, much longer enhancement than the frequency.
You mean if it is rotating?
No, if it's not rotating.
If it's not rotating, it's only 1/10, I think, no? The slowest decaying.
So they come out, the standard one come out, the quasi-normal mode, and then there are.
Oh, your thing.
Yes, and then there are additional stuff that comes later with a much lower frequency and a much longer lifetime. So the amplitude is much smaller compared to the standard. In that sense, they are, if you wish, if you want to say, they are invisible. When the black hole is rotating, a small miracle happens because the frequencies of these additional quasi-normal modes are spun up to 2 times the frequency of the rotation of the black hole. And so if you observe the actual merger, you will be able to observe them, but the lifetime is much longer. And so in this case, the amplitude of the quasi-normal modes is lower. But as I was emphasizing all the time, what is important is the total energy that is channeled into these additional modes. So in that case, the differences are not order 1. They are small corrections to the standard GR. In the merger, I don't know, but I expect, because of the arguments that I was presenting, that the difference will not be that large. There will be some difference, and to actually be able to get to the point that it can be done, I have to be able to find a model that can be well posed in the sense of gravitational, numerical gravitation, and then see what happens. And I'm trying to do that, but as I said, I expect that it will not be a killer.
I had a quick question
Yes.
about your claim about how this would arise. Were you saying that in string theory, that's an example of a
No,
model? Which
I have a model of highly excited strings where I can estimate this type of
But
quantity.
it's a kosher model in the sense
Well,
that
it depends.
another string theorist wouldn't say a spiking rate.
Yeah.
Oh, okay, thank you. That answered the question.
Yes.
So for the moment, we don't know that there's a consistent physical model
Yes.
that would admit this. But of course, it's definitely something they should look for.
Right. So we are trying to approach this from various points of view. For example, we're trying to create models that are based directly on string theory to do that. And there's a recent activity related to the models that I described, condensates of winding modes of strings. And so
If there are no more questions, let's take a round again.
Are you it sounds like you're a classicist, Andre.
Classicist, yes.
I was gonna say, just talking there, that when we're investing money and making bets.
It's a 12 surface, so that means there is no color. Ah, there is no color control. Okay, so we can start that doesn't need that much time.
But we have 130. Well, it's more than 145, but then I
Probably.
yeah, we can grab that together.
Yeah, we can do that. We can if you want to.
Yeah.
That was really nice and clear. Thank you.
Basically, one.
after I answer your question.
You have a lot of
Well, I just,
More confident have a chat.
I've
Well, because just
taken
started.
up the